Hello, my name is Andy Brazier and I've put together this short video to show you how to carry out human error analysis, or HTA. It may help if you've watched my video on carrying out hierarchical task analysis before you watch this one, although this is not essential. So what is HTA? It is a systematic way of identifying the errors or human failures that may occur when a task is being performed. By using a checklist or prompt sheet, we make sure that all credible errors are considered, rather than focusing on the most obvious. We can then record the likely consequences of the errors and details of any risk controls that we may have in place. We can also consider what else could be done to further reduce the risk. HA is particularly useful because it provides us with a simple and effective method of looking at the complex and often problematic issue of human error. A number of different names have been given to HEA over the years. Examples: fear, Sherpa. It's sometimes called a task or procedure HAZOP, where HAZOP is a well-known technique of assessing hazard and operability of a system. To be honest, these are all essentially the same and tend to use very similar prompt sheets, use the same approaches I'm going to talk about today. We carry out HEA by looking at a specific task. A good starting point then is a completed hierarchical task analysis for that task, and it is very convenient to develop the HTA and the human error analysis at the same time if you can. If you haven't got an HTA, an existing procedure can be used, although with caution, because few procedures are really that well written and often don't reflect how a task is performed in practice. You can just brainstorm activities and apply HEA there, but it's not really particularly systematic and may not result in a very useful outcome. Once you have the information about the task, your other requirements are fairly simple. You will need to generate a table to record the results, which you can do directly onto a computer spreadsheet or word processor table, or you may create some sort of printout that you'll use during your analysis. The table can be adapted to your needs, but you'll probably need a minimum of 5 columns. The first column will be used to record the task step being considered. The second will be used to record the potential errors or human failures. You will want columns for consequences, existing risk control measures, and to make notes about any additional measures you may want to propose as a result of your analysis. The way you fill this in, I'm going to show you later. As well as your table, you're going to need a checklist of human error types. This makes sure that you consider all the possible errors that may occur in the task you're looking at. This is a fairly typical checklist that you can download from my website. It identifies different types of activity, so that's actions, checks, selection, planning, information retrieval, communication. And for each it gives you some examples of the types of errors that can occur. If you take a simple example, say opening a valve, that's an action, so that's the part of the table we're going to use. And it prompts you to think, well, omitted, if that step is omitted, what is the consequence if we don't open the valve? What about incomplete? Is there a consequence if we don't open the valve fully? What about right action on wrong object? That means what happens if we open the wrong valve? Or wrong action on the right object? We go to the right valve, but we close it instead of opening it. Is there a consequence if we open it too quickly or too slowly? What about misaligned? This is typically associated with putting things together correctly, so maybe not a factor in this task. And you can work your way through the rest of the error types. Okay, so once we've got our table and our prompt sheet, we're either going to need a pen and paper, or you can record your results straight onto the computer spreadsheet or table. In fact, it is best to perform human error analysis with a team, involving a number of people who are familiar with the task. Using a computer linked to a data projector is a great way of doing this, allowing everyone to participate, and meaning your results are recorded in a usable format with a minimum of additional work. To analyse a task, we're first going to select a step from the task that we're interested in. We're going to determine what type of step it is. Is it an action? Is it a check? Etc. We then look at the checklist and look at which of the errors for that type of step apply. Going to consider the consequences of those errors, think about the existing risk control measures. What have we got in place to protect us against those errors, either to stop the error happening or to protect against the consequences? And we're going to think, is there anything else we can do to reduce the risks further? This is an example of a hierarchical task analysis. The task in this case is transferring fuel from a road tanker to storage. You can see there's a number of activities there. Some of those we've broken down into hierarchies of levels of detail. I'm going to pick a few steps from the task and show you how we carry out an HEA. Take 2.1, it's connecting earth to the tanker. This is something we do to prevent static build-up, which can start fires. If we look at what type of step it is, we can go through the list of possibilities, and in this case we'd say it's an action. So, once we know what type of step it is, we can then look at the potential errors. So under action failures, we've got a few to select from. We can admit the step, it might be incomplete, we might do it to the wrong object, the wrong action seems unlikely, doing it too quickly, too slowly. We might misalign it, we might do it too early, too slow. The rest of the errors probably not appropriate in this case. We now start filling in our table. In the first column we write down the task step, connecting the earth. We then start to go through the error types. Let's start with action omitted, and we make a note of what that really means, failing to achieve an earth before starting the transfer. We then say, what would the consequences be? Well, I've already explained why we attach an earth in the first place, so we can say, well, if we don't do it, there may be a static discharge that may start a fire. We then go through and say, well, how do we control the risks at present? Well, one thing we might refer to is, well, this is standard practice. All tanker drivers will know about attaching an earth, and so there's no real reason to think they wouldn't do it in this case. We may also say, well, the earth connection is readily available. It's nice and convenient. It's not like they have to go and hunt around, which may mean it's more easily overlooked, or that people won't necessarily bother. But we might say, well, is there anything else we can do? And there's certainly technology out there that you can interlock these earth connections. It wouldn't allow a transfer until an earth has been established. Obviously there's financial implications, but it's maybe something you would recommend on the basis of your analysis. So we make a record of that in the final column. Well, we've been through one error type now, but we have to remember that we did identify some other potential error types. For example, incomplete, wrong object, misaligned, too late. Now, the reality in this case is probably they're all pretty much the same error. We will fail to achieve the earth before starting the transfer, so all the other information we've collected for this task step is applicable, and we'd probably say we've done enough and we should move on.